Hey guys, today we're going to get started on our notes on tree diagrams. We're going to just jump right into some rules and then do a few examples. First things first, we need to learn our general multiplication rules, which tell us the probability of an event A and B occurring is equal to the probability of event A times the probability of event B given A has already occurred. And this is a conditional probability. Remember, that means given. If the events are independent, then the probability of, B given A is the same as the probability of B. So, the probability of A and B is just the probability of A times the probability of B. For a tree diagram, what we should notice is that we have two mutually exclusive events, probability of A and the probability of A not. Then based off that first event, we've got another option. And that is event B or C. These are conditional probabilities. The probability of event B given A, probability of event C given A, probability of B given A not, and probability of C given A not. One rule about tree diagrams is as you multiply the probability times the given probability, just like here, we get the intersection. My puppy is acting up.
Let it go. Let it go. Back.
All right, so as we multiply probability times conditional probability, we get the intersection via that general multiplication rule. One thing to remember is that these are conditional probabilities inside this part of the tree diagram. Let's look at this first example. A computer company makes desktop, laptop, and tablet computers at factories in two states, California and Texas. The California factory produces 40% of the company's computers, and Texas makes the rest. Of the computers made in California, 25% are desktops, 30% are laptops, and the rest are tablets. Of those made in Texas, 10% are desktops, 20% are laptops, and the rest are tablets. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center and observe where it was made and whether it's a desktop, laptop, or tablet. So our first event is where those laptops are made, or computers, sorry. They're either made in California or Texas. It tells us 40% are produced in California, so 60% are produced in Texas. Now, those are either laptops, so this is the probability of a laptop given California. They are desktops, or, oh wait, I got confused. Desktops laptops, and tablets. Okay. The probability of a desktop from California is 0.25. Laptops from California is 0.30. And tablets are 45%. We're going to do the same thing now for Texas. The probability of a laptop from Texas, a desktop from Texas, or a tablet from Texas. 10% are desktops, 20% are laptops, and that means 70% are tablets. And we can calculate these intersections here. We've got California and laptop. We've got California and desktop. California and tablet. Texas and laptop. Texas and desktop. Texas and tablet. And we're going to get all of these probabilities by multiplying across. 0.4 times 0.3, 0.12. 0.4 times 0.25, 0.1. And we're going to just keep going along the entire tree diagram. All right, now that we have our tree diagram filled out, now we can answer some questions about probability. So the first question is, find the probability that the computer is a tablet. So probability of a tablet. Now notice we have all of the tablet data tied up in here with conditional probabilities. The law of total probability tells us that we can just add the intersections, a tablet in California or a tablet in Texas, and we can find out how many are tablets. So we can go ahead and add those intersections. 0.18 plus 0.42. So 60% are tablets. So if you're looking for the probability of an event that is tied up with conditional probabilities, to find the probability of that event, you look at the intersections involving that event. Okay. If we select 4 computers at random from the distribution center with replacement, what is the probability that at least one of the computers is a tablet computer? So probability at least one is a tablet is equal to 1 minus the probability that none are a tablet. So we could look at 1 minus 0.4 times 0.4 times 0.4 times 0.4. When you're looking at least, it's kind of easier to look at 1 minus the probability of 0. This is 1 minus 0.0256. That's 0.9744, 97.4%, which makes sense. At the bottom, it says probability given that a tablet computer is selected. What is the probability that was made in California? So we don't have that right off the tree diagram. If you notice, these are given condition California and Texas. So if these are rule of conditional probability, which is the probability of California and Texas and tablet, or the probability of a tablet. So California and tablet probability up here is 18% over the probability of a tablet, which is 60%, which is 30%. So we're at kind of combining all the rules we've learned. Let's go to the next page. A factory production line is manufacturing bolts using 3 machines, A, B, and C. So we've got machine A, machine B, machine C. A is responsible for 25%, machine B is responsible for 35%, and C is responsible for the rest, which would be 45%. Not 45%. Just 40%. It says it's known from previous experience that the machines, with the machines that 5% of the outputs for machine A are defective. So right here, we've got defective is 0.05 and not defective is 0.95. Machine B, 4% are defective, so 96% are not defective. And down here for machine C, 2% are defective, and so 98% are not defective. Now let's find all these intersections. A and defective, A and not defective, B and defective, B and not defective, C and defective, C and not defective. And we're going to get all of these probabilities. One rule about all of these intersections, maybe we didn't say, is that they should all add to 100%. Alright, so we've got all of our intersections here. And now the question says, a bolt is chosen at random from the production line and found to be defective. What is the probability that it came from machine A? So we're trying to find the probability of A given defective. So right here, remember, this is the probability of defective given A. So we don't have that. We can find it though. A and defective over the probability of defective. So let's find the probability of something being defective first. That's 0.0125 plus 0.014 plus 0.008. And that's going to be 0.0345. And the probability of A and defective is 0.0125. So 0.0125 divided by 0.0345 is approximately 0.3636%. The next question is the probability of B given defective. So that's B and defective. Over the probability of defective, which would be 0.014 over 0.0345. Which is approximately 41%. And last but not least, part C. I'm going to do it over here. Probability of C given defective, probability C and defective over the probability of being defective is going to be 0.008 divided by 0.0345. Which is approximately 23%. All right, I'm going to pause the video. You do number 3 and then unpause to check your answers. All right, everyone, and here's your answers. We got all of our given conditions, probabilities, all of our intersections. These all add right here to 1. That's a good way to check. And then we've got our conditional probabilities that we were asked, which was lost given a particular airline. We use that formula for conditional probability to get all 3 probabilities.